Okay, good afternoon, everyone. At first, I would like to thank the HKS committee to provide this opportunity. My name is Zhang Ke from EE department, and my supervisor is Dr. Wang Chen. So my topic today is lithium niobate photonics for power efficient data links. So at first, I would like to talk about optics communication. The word optics means light. We know that light is the oldest way of transmitting information. Thousands of years ago, we used smoke. We know that an enemy is coming when we see the smoke, but the data rate is quite low. Let's say about 1 bit per hour. And now we use optical fiber to communicate. The data rate can be higher than 1 terabit per second per fiber. However, both the smoke and the optical fiber, we transmit data at the speed of light. So in modern communication, usually we have the electrical signal. Our phone and our computer, they are all use the electrical signal. So first, we need to convert the electrical signal to the optical signal. And next, we transmit the optical signal using the optical fiber. And finally, we convert the optical signal to the electrical signal. Here, the key component is a modulator, which can convert the electrical signal to the optical signal. And the word modulation means light switch. So in modern communication, our goal is to switch light on and off in a faster, cheaper, and less power consumption way. However, for the commercial modulator, it is a very high power hungry. Also, it is expensive and in large size. So the question is, can we have a cheaper modulator with a better performance? So before answering these questions, we need to know how a modulator works. So a modulator is based on EO effect and Mach-Zehnder interferometer structure. The MZI structure means that initially we have a light coming in, and then the light is split into 2 arms, and finally the 2 arms will combine together and interfere with each other. And when we apply voltage to the material, due to the EO effect, the index of the material will change, and the change of the index is proportional to the E field. So by changing the voltage, we can change the output. We can change the output of the. We can change the output intensity, which means that the output light is modulated. Here, a key parameter is V pi, which means that the voltage applied for pi phase shift. Okay, so if we look at the cross section, we have optical waveguide, we have ground signal, and ground electrode, and the signal electrode. So the E field is equals to voltage over D. Very simple high school physics. So the optical mode is realized by the total internal reflection, and this is realized by a low index cladding and a high index core. So the light will confined in the high index core. We call this optical mode. But for the commercial lithium niobate device, the waveguide is formed by the ion diffused core and the intact lithium niobate cladding. This leads to a very low index contrast and a mode size about 10 micron. So here we use the thin film lithium niobate. The idea is that for the vertical direction, it is a thin film, and we only need to care about the lateral direction. So in this way, a high index contrast can be realized, and the mode size is very smaller. So if we do a comparison about the mode size, this is a commercial one, a very large mode size, and for the thin film, we can see this is a very small mode size. So the good news is that for the vertical part, we don't need to do something because this is commercially available. This is not an advertisement, but we can directly buy this lithium niobate on insulator wafer, and sub-micron thin film can be achieved. So we only need to care about in the lateral part, and this was achieved by etching process. Firstly, we have a mask, and then we transfer the pattern from the mask to the lithium niobate. However, lithium niobate is a hard to etch material. Also, during the etching process, we also suffer from the surface redeformation. So it is not easy work to etch lithium niobate. This picture shows that in 2007, the etched lithium niobate, you can see that there is a very rough surface, and then after 10 years, a very smooth wave bed with low loss can be achieved. So in the next year, a CMOS driving modulator is fabricated. This is the integrated lithium niobate modulator. We can see that the wave height is very low, about 1 volt. So the lithium bait can directly driven by a CMOS. On the contrary, for the commercial one, the wave height is very high. So an electrical amplifier are necessary. This picture shows the commercial one modulator and our chip. We can see that our chip is very small, also a very high bandwidth and CMOS driving voltage, and of course a very high power reduction. So this is due to the smaller gap and the increased EO efficiency. So we can say that the fab quality determines the performance. So how to evaluate fab quality? Usually, we use a whisper gallery mode resonator, and we have a Q factor. The name whispering gallery comes from the architecture. The Q factor is defined by the energy stored in the ring and over energy loss. So this means that if we have a high Q factor, this means that more energy is stored and a low energy loss. This picture shows that the Q factor improvement with year passed by. We can see that there are some red circles. These are done by Dr. Wang at Harvard University. So you may have a question. What about at CTU? Okay. Initially, we don't have the same advanced equipment as Harvard, but we could do some optimization. Our work shows that even use the metal mask, this could also lead to a high Q resonator. This picture shows the normal metal mask. By a lift-on process, we can see that there are some fencing and roughness on the sidewall. But after optimization, a very smooth sidewall can be achieved. And then use this metal mask, we do the etching, and a very high Q, about 1 million, can be achieved. So now at CTU, about 2 million Q can be achieved. Also, we have explored this wafer scale lithium niobate process. This picture shows a 4-inch lithium niobate wafer we fabricated using a simple UV lithography at HKUSD and CTU. So if we zoom in this part, we can see that there are many structures here. And this part is our modulator. So except the modulator, we can also fabricate other structures such as the micro ring and the micro racetrack, also delay line and directional coupler array. So now our work shows that a very low loss across the whole wafer can be achieved, and also 6-inch wafer are ready. So based on this fabrication process, now we can do something about data links at CTU now. So in the data links process, in the data links system, a very important idea is the WDM, wavelength division multiplexing. So initially, usually, we have different kinds of information to be sent. So if we use individual fibers for per channel, this is a very huge waste. So usually, what we do is first we combine this multiple channel together. And then when transmit this information via one fiber, and finally we separate these channels. So this is called WDM. We can see that this is very economic, power efficient, and widely used. So if we look at the WDM system, K is the light source with different frequency components. So if we do a transformation, maybe more transformation, we can get like this. So this looks like a cone. So we call this optical frequency cone. And optical frequency cone means that in the frequency domain, there are many equally spaced cone lines. And in the time domain, it is optical pulse. So the frequency cone is so important that these two guys shared the Nobel Prize due to their contribution. And the question next is how to generate frequency cone. If we only have one pump line, we can only get one individual frequency component in the frequency domain. So a very straightforward way is we can use many lasers with different frequency, such as 300 lasers or 500 lasers. But I don't think that people will do like this. So usually we use this phase modulator. The idea is if we have a pulse line and we do a EO modulation, this pulse line will generate two sidebands. And if we increase the modulation, there are more sidebands will be generated. So this is the cone generation. This picture shows the cone generation. We are very high power. We can see that 40 cone lines can be generated at a very high power. So what we think is, can we do a phase modulator with less power? So if we look at the cone generation, we found that the light comes in, modulated, and comes out. So this is the one-pass EO modulation. So here we propose a multi-pass modulation. The idea is that the first light comes in, modulated, comes out, and then the light will come back, and undergoes the next modulation. So this is the multi-pass modulation. So in this way, a higher modulation can be achieved, but with the same electrode structure and power. which means that if we want the same modulation, less power is needed. So this picture shows the structure of our multipass EO phase modulator. Initially, we have light comes in and EO modulation and comes out in TE mode. And then we have a mode converter. This T1 mode will undergo the second modulation. And then this TE mode will convert to TE0 mode and come back together. This is the third EO modulation, and then the fourth EO modulation. This is a little bit complex. So for this modulator, a key component is a mode converter and the crossing part. So we designed this cascaded mode converter to evaluate the mode converter part. We can see that if the light comes in from the upper port, it will go out from the upper port. If the light comes in from the lower port, it will go out from the lower port. This picture shows the measured result, and the result shows the mode converter has a very low crosstalk. Also, for the crossing part, our result showed a very low loss, about 0.2 dB per crossing. So this multipass modulator has a very low wave height and a very less power consumption. In theory, we can have 16 times power reduction at most. So this is a power efficient phase modulator. Also, we can also have the cone generation via this resonator. The idea is that if the EO modulation is equal to the FSR of the ring, the EO modulation will be enhanced. This picture shows the device, shows the structure of the device, and this is the result. We can see that there are many cone lines. And here, more than 900 cone lines are generated, and the power is very low, less than 1 watt. And this could be further reduced to about 30 milliwatt by some optimization. At CPU, still we are working on this part, but this is a very technical, but it works. And now we are working on the optimization. Okay. So with the modulators and the frequency cone generation, what we want to do is a WDM system on one chip, which means that we want to combine this optical frequency cone generation modulators together on one chip. This picture shows a schematic of the chip done by Luxon's group. We can see that first we have a light comes in, and using a silicon nitride chip, optical frequency cone can be generated, and then the cone was sent to a silicon chip, and the cone lines will be separated by this the interleave, and then each cone line will be modulated, and then we combine this cone line together, so we can see that this is the picture of the chip. We can see the structure is quite complex, but the chip is very small. And what we want to do is we can, by the lithium nanowave platform, we can combine this part and this part together. Also, due to the excellent performance of lithium nanowave, here we can do the high-speed EO modulation. So on the lithium nanowave platform, we can also do the microwave photonics. Microwave photonics means that we use the optical device to generate, transport, and measure the high-speed RF signals. This picture shows the radio over fiber links. Initially, we have a radio signal comes in and antenna modulator and fiber and PD. So this is a very huge system. For this ideal chip scale microwave photonic system, there are two important ideas. First is a very low loss signal processing network, and another is a high performance EO modulator. The word high performance means that a very highly linear modulator, which can faithfully convert diagonal microwave signal into optics. So, so for the traditional MZI structure-based modulators, we can see that the output line has a sine-like profile, which is not linear. So, but we look at the micro ring. We look at the ring resonator. What we can do is that we can have different phase, but without lose the optical intensity. So what we do is we can combine this together, which means that this is a ring-assisted MZI modulator, RA-MZI. So in this way, we can see that the output spectrum have a very linear profile. So this picture shows the structure, and the right-hand picture shows RA-MZI. We can see a very linear spectrum. As a comparison, we can see that MZI have a sine-like profile. Our measured data shows that about 18 dB improvement in the linearity over the reference MZI. So this is a very good work. And this is achieved by the lithium dioxide is an intrinsically linear material response, and also we use RA-MZI this structure. So also we can do this millimeter wave photonics. Previous work has the bandwidth about 100 gigahertz. So in the future, what we want is in the millimeter wave and even in the terahertz. The millimeter wave is very useful. It can be used in the 6th generation communication LiDAR imaging. So if we can do a modulator operating at this bandwidth, it will be very interesting. So for the question, can the modulator go in faster? The answer is yes. They always simple, but this is more difficult because millimeter wave is harder to control. However, by some optimization, we realize this millimeter wave optic modulators. This picture shows the measured data. We can see that about 175 gigahertz bandwidth, 3 dB bandwidth is achieved. Also, for the 6 dB bandwidth, it is close to 300 gigahertz. And for the VPI, at 250 gigahertz, the VPI is about 6.3 volt. So this was measurement at the sticky lab. Okay, so let's do a quick summary. First, I have shown the low loss lithium niobate circuits, and next I have shown the multipass EO modulator, and also a high linearity EO modulator, and also the high speed EO modulator. So also we have a outlook. So in the past, we have vacuum tubes, and with the improvement of silicon nanophotonics, we can fabricate a chip which lead to the electronic revolution. And now we have traditional optical components, also nano fabrication, and now we can achieve the high performance integrated photonics circuits. So hopefully this can lead to a photonics revolution. Okay, that's all for my talk.